Thank you for the introduction. So here's kind of the overview of why you should care about data orderings for stochastic gradient descent. You're hopefully all familiar with stochastic gradient descent, right? You have some objective. The objective is typically written as a sum of sub-objectives over a data set. So in machine learning, this is typically empirical risk minimization. F is our total loss. F of W semicolon X by abusive notation is the loss for an example X. W is our parameters, our weights, and what we are trying to minimize is the average loss over some data set D. And we do this by drawing an example XT from the data set, updating with just the gradient computed for that one example XT, and then just repeating this many times. And over time, we hope that this decreases the value of the overall objective that we care about. So every time we're drawing a single example, we're improving the parameters using that one example. And of course, what we actually run in practice is something more complicated than this. We use a mini batch of examples, a group of examples, but the basic idea is still the same. And often, especially in vision applications on small data sets, we actually do something even more complicated than mini batching called data augmentation, where rather than drawing examples from a data set, we instead draw examples from the data set and then randomly modify them with what's called an augmentation. So for example, we might have an image, we might flip it at random, we might crop it at random, we might rotate it by a random angle to produce something which we believe is a example from the same distribution and would have the same label, but which might give us more variety in our data. But within all of these algorithms and with all of these settings, there's the question of how to select the order in which we use the examples. How do we select the sample order x0, x1, x2, etc.? There are a bunch of things that are popular for people to use that we see a lot in the literature. Perhaps the most commonly used method in theoretical papers is just independent random sampling. So every time you draw an example from the data set, you suppose that it's drawn completely at random independently from the data set. This, for example, is the version that I teach in my intro machine learning class. When I teach the intro machine learning class, it's really easy to analyze. In practice, this isn't what we run most of the time. It's more common to run something else. One popular approach, which people sometimes use in practice, is called incremental gradient, where you just sample the data cyclically in the order in which they happen to appear. So you imagine that your data set is ordered, and you just draw the first example in the data set, then the second one, then the third one, and when you get to the end, you just repeat. And this can leave practitioners open to issues that would happen if your data is somehow sorted or in a strange order that might be bad for learning. So it's more common, rather than doing incremental gradient, to do what's called shuffle once, where you choose a random permutation of the data set and then just run incremental gradient on that. And probably the most popular, actually certainly the most popular example selection method that is used in practice and a default in both PyTorch and TensorFlow is random reshuffling, where you're selecting examples without replacement from the data set. And it's basically called random reshuffling because this is equivalent to choosing a new shuffled order for your data set at every epoch. So every time you pass through the data set, you choose a new order for the data set to be passed in, but you don't use any example twice until you've used every example once. Now, there are some other methods that people use that are more sophisticated than this. Probably the most significant among these is curriculum learning, which is a training strategy where rather than randomly using the training examples, you instead order them in some way that is designed to improve generalization and improve learning in a way that is sort of analogous to the way we present concepts to humans who are learning, where we would typically start with simpler concepts and then move to larger numbers of concepts and more complicated ones. And here, This is a more complicated question. This kind of lies outside of the question of large-scale optimization. It lies outside of the question of actually minimizing a loss. And so because of this, even though I want to mention this is a really significant related line of work, it's not going to be the subject of this talk. So I'm going to focus on these other example orders for which we can say something about how that example selection impacts the rate of convergence of stochastic gradient descent in theory. And for a long time, random reshuffling was just a thing that people used in practice where they believed that it caused it to converge faster. And there were a lot of papers pointing this out. But where we didn't have good theoretical understanding for why or even whether in theory it worked better. And relatively recently, I mean, maybe not relatively recently compared to like the timeline of machine learning where people called 2020 the ancient history, but relatively recently in terms of like my age, we've had these new theoretical gaps showing gaps between width replacement SGD, that is just draw everything independently at random, and random reshuffling. And here's just an illustration. There are actually many gaps in different optimization settings, but for non-convex optimization on a objective where the gradients are L Lipschitz continuous, then after t steps, and this is steps of gradient descent, not epochs, on a data set of size n, you have a gradient magnitude of 1 over the square root of t for width replacement stochastic gradient descent. That's like the standard rate that you get for non-convex optimization. Where here we're measuring the magnitude of the gradient of the objective. That's the standard metric that we use for non-convex optimization. And for random reshuffling, this rate is somehow improved to big O tilde of n to the 1/3 over t to the 2/3. And so the exponent of t is larger, and this suggests that after you're running a number of steps that is large relative to n, you start seeing an improvement of random reshuffling over with replacement SGD in theory. And this matches what people observe in practice. And there are a bunch of other gaps in other settings, although one caveat of some of these gaps is that it's only in the strongly convex and quadratic cases that we know good lower bounds to match these gaps. So the gap that I just presented to you in the non-convex setting is really only a gap in the sense that we have two upper bounds and they differ from each other. We don't know that those upper bounds are both tight. But it's still very suggestive. Okay, so this is all very interesting. And we set out like a year or so ago, maybe more than a year ago, year and a half ago, to look at this question of what is it about this order that makes it converge faster? Because we want to be able to generalize these results to more, different sequences that we might get in practice. And just to give you an illustration of why I, a person who identifies as a machine learning systems guy, might care about this. In a lot of settings, we are running distributed SGD or decentralized SGD, where examples are located on different computing devices, different workers. And we often don't want to just completely randomly shuffle our data, because doing this would involve a all-to-all communication where different workers send data to each other. We want instead to be able to run example orders that happen to be efficient to run based on where the data is stored on a worker. And while there are loads of those, it's not like that all example orders happen to be efficient to run. And so we'd like to be able to say, well, is there some way that we can relax random reshuffling to consider only some possible orders and still maintain the theoretical guarantees? Okay, so we wrote this paper in 2022, which is, I think, Ancient History by Machine Learning Standards. And the main insight is that the thing that it is about the random reshuffled example ordering that makes stochastic gradient descent converge fast on these example orderings is that for random reshuffling, averages of consecutive gradients, or averages of consecutive example gradients, converge to the full objective gradient faster than for independent with replacement sampling. And more generally, if you want to analyze a example order, if you want to analyze a sample order and figure out and predict how fast SGD is going to converge, it kind of suffices to reason about how fast averages of consecutive example gradients converge to the full objective. And so just to give some illustration, for with replacement sampling, that is, every time you draw an example, you draw it independently at random from the whole data set. These are just going to converge to the full gradient at the classic Monte Carlo rate of big O of 1 over square root of m. That should be fairly obvious. It's because we're averaging a bunch of independently drawn things. Well, when we average a bunch of independently drawn things, they're going to converge to their expected value at the rate of big O of 1 over square root of the number of things we drew. However, for random reshuffling, we actually observe a slightly different rate, that for large enough m, that is, if you're drawing a large enough subsequence of the example sequence, the average of the gradients will approach the full batch gradient at a rate that scales like big O tilde of square root of n over m, where n is the number of examples in the data set and m is the number of gradients that you average. And you might think that this is, requires some complicated proof, but it's actually very intuitive if you think about what happens as m becomes larger than n. So when you're averaging a sequence of examples or when you're averaging a sequence of gradients of examples that are drawn via random reshuffling, and the number of examples that you're drawing is much larger than n, what you're going to get is you're going to get some examples that are from the last part of a first epoch, a bunch of full epochs, and then some examples at the end that are from the first part of a last epoch. And the key insight is that all of those examples, or all of those epochs in the middle, because you're drawing every sample from the data set once, the error from those epochs is going to average out to 0. Because if you average out all of the examples you draw over an epoch, that's a perfect estimator of the full batch gradient. And keep in mind that here, for this analysis, we're assuming that the parameters aren't moving around at all. So you're just evaluating the gradient at a single parameter value. And so then it should be more clear. And this is why you get this faster rate. And what's interesting about this, and I think I have this on the next slide. Yeah, what's interesting about this is that it kind of seems to relate to the faster rate that you get from random reshuffling versus with replacement SGD. So in particular, for with replacement SGD, you get this consecutive example gradients converge to the full gradient at a rate of 1 over square root of m. And, well, that happens to be almost the same rate, except we replace the m with a t, that non-convex SGD converges at. And similarly, for random reshuffling, this turns out to not be exactly the same as a difference. But if you compare these two rates, it seems like for random reshuffling, what you do, or what the effect is that you multiply the numerator by some power of n, and then you divide the denominator by you multiply the numerator by some power of n, and you multiply the denominator by that same power of m, or t. And we can actually make this insight rigorous. So under the, we need to make a couple of assumptions. So the first assumption we'll make is L smoothness. So this is just standard gradient is L Lipschitz continuous. And then I'm going to add this new assumption, which is a bound on the average gradient error, where I'm going to say for some constant C, for some constant gamma, which is between 1 and 2, and for all weights values WT that we might see over the course of running SGD. This bound holds, so the averages of consecutive gradients converge to the full batch gradient at a rate that depends on the number of gradients that you're averaging, bounded by the quantity c squared over m to the gamma. Then we can prove that using SGD yields a gradient norm that is bounded by big O tilde of c to the 2 over gamma plus 1 times L to the gamma over gamma plus 1 times T to the gamma over gamma plus 1. And with a little bit of substitution for different values of gamma, you can see that this actually unifies the analysis of both methods, so it recovers the correct rate for both width replacement SGD and random reshuffling. But it also greatly expands the class of sample orders that we can analyze. So any sample order for which we can reliably say something about how fast averages of consecutive example gradients converge to the full batch gradient, we can automatically use that and get a proof of convergence of SGD. And this is really useful because it immediately lets us recover old and new rates, sometimes rates for things that haven't been analyzed before, and even rates that are potentially better than what has been done. So for example, we recovered a classic rate for permutation SGD. We got a rate for shuffle once, which is faster than what was previously available in the literature. We got new rates for random reshuffling-like methods. One method that we tried was random reshuffling with data echoing. This is a method that has been proposed that basically repeats each data example multiple times. So rather than taking one step with an example and then drawing a new example, instead it takes 2 steps with a single example, or it takes 5 steps with a single example, or it takes, that's a parameter of data echoing. And we were automatically able to show that data echoing inherits the faster rate of random reshuffling when this previously wasn't known. And we also got improved rates for methods that aren't permutation methods. So one of the methods that we studied was Markov chain gradient descent, which is a method that draws its examples from the state space of a Markov chain. So there's actually some correlation or some dependence between the examples that are drawn. This is pretty popular in Bayesian inference, and we got better rates for this method than were previously known. Okay, I
have a question.
Yeah, if there are any questions, definitely now is a good time to stop and ask them.
Yeah. So you listed several methods here, right?
Yeah.
So for all these kind of permutation or shuffle or once or even this Markov chain gradient descent, all
Yeah.
this kind of sampling method will satisfy your average gradient error bound?
Yeah, basically, yes. And it's because this is a very generic bound. So you can basically show that for any of the permutation type methods, this will hold for some gamma and some c. And for the permutation type methods, gamma will generally be equal to 2. And for the stochastic methods like the Markov chain method or just regular old independent draws, gamma will be equal to 1. And the real trick is to figure out what c is.
Right. And also here, this bound looks like you don't take the expectation, right? It's something deterministic then, right?
Correct.
So does that mean you need some boundedness on maybe its iterates?
Yes. So what we're typically doing here is we're going to, the way that the theory actually works for these randomized methods is that we say with high probability, the sequence satisfies this bound when we have a randomized method. And then in order for that high probability bound to hold, we will need C to be somehow dependent on the logarithm of the number of examples that we draw.
Okay. But that C may be big number, right?
C might be big, yes. I mean, it's not as if C is like a global constant. C is going to depend on problem parameters. So it might depend on the variance of the gradients. It might depend on the size of the data set.
Okay.
So it definitely can be big. And yeah.
Okay. Thanks.
All right. So one thing that we wanted to apply this method to, but turned out to be a little bit tricky, is data augmentation. So remember at the start of the talk, I said something about how sometimes we draw an example at random, and then we randomly transform it by, for example, flipping it or rotating it or cropping it in a random way. And the problem is that when we set up this data augmentation problem where we're trying to minimize the loss, except now the loss is not only taken an expectation over a draw from the data set, but it's also taken an expectation over a draw from the random augmentations that we might do, this setup becomes inherently stochastic. And so one thing that we looked into to try to avoid this, because if we just tried to put in a data augmented example sequence into our existing theory, it would just yield the same rate that you get with replacement SGD. So we wouldn't get any acceleration even if you use data augmentation with random reshuffling. And so what we looked at is using what's called quasi-Monte Carlo sampling instead of random sampling. So here, quasi-Monte Carlo sampling uses a low discrepancy sequence and has this property that it converges at a rate of big O of log m to the s over m, rather than the rate of 1 over square root of m, typical of random sampling. So, averages that you're making using quasi-Monte Carlo estimates are somehow more well distributed over the space than Monte Carlo estimates, than random draws, and so they're able to converge faster. Now, the trick here is this parameter s, which I haven't defined, and turns out to be the dimension of the space that you're sampling from. And you might think, well, clearly, in machine learning, this is going to be a complete non-starter because the dimension of our problems is very large. So log m to the s is going to blow up tremendously, even if m is small. And that's a reasonable thing to consider. However, the key insight that lets us use this for data augmentation is that s is only the dimension of the thing that we're sampling from, which is the dimension, in this case, of the space that the data augmentations live over. So, concretely, if I'm doing a random rotation, even though I might be rotating an image that has, hundreds of thousands of dimensions, the space that the rotation is described by is just a single angle. So it's actually one dimension, and s would be 1 here. If I'm doing a crop is described by 4 points, so s would be 4. And so for typical data augmentation values, this is a single digit integer, s, and so this is actually tractable. And we can run this and make SGD converge faster. And what we observe is that when we replace data augmentation via, excuse me, we replace data augmentation via random sampling with data augmentation via quasi-random sampling, via quasi-Monte Carlo, we can actually get some real empirical improvements. So here I'm looking at validation of ResNet 20 on CFAR 10, which is a relatively small scale data set. And we can observe that when we replace our regular independently drawn at random uniform data selection method with quasi-Monte Carlo, we already see a significant difference in validation accuracy and validation loss. So it already improves a little bit. And the key insight here is that that's even without doing any different hyperparameter search. So if we just do this replacement and use the same hyperparameters that were tuned for the IID uniform, we already get an improvement. And then if we redo the hyperparameter search using quasi-Monte Carlo as our method, we get a significant improvement. So here we're getting something that's on the order of almost a 0.5% of improvement, which is great for a method that's essentially free. And we similarly get a little more than 0.5% of improvement on ResNet 18 on ImageNet. And I do want to be clear here. It's not as if this is like a tremendous improvement. It's not like you're going from 70% to 90% automatically. But the nice thing is that this is a method that generally works across a wide range of settings that has some theory behind it and that is basically free to run. And it comes alongside some theoretical bounds, so we're able to show that when we use quasi-Monte Carlo with data augmentation, we improve the rate of convergence from something that goes like 1 over square root of t to something that goes like 1 over t to the 2/3, which is really nice. Okay, so that's all pretty good. It's good to be able to get these couple of 0.5% improvements, but can we do better? And in particular, not everybody uses data augmentation, and for somebody who wasn't using data augmentation, the previous paper, well, it gives us some insight into why random reshuffling works, doesn't actually tell us what we maybe should use instead of random reshuffling. And there's no good reason to believe that a random ordering is necessarily always the best. So in a paper from last year's NeurIPS, we looked at how we can use this insight from the example ordering paper that I just described to find data permutations that are better than random reshuffling and that let us converge faster. So how do we do this? Well, the insight is that if this average or convergence rate of gradients averages to the full batch gradient is the thing that we care about in terms of how fast we're going to converge. Why don't we just try to choose the order we use the examples in order to minimize this running sum? And so that's what we're going to do. For technical reasons, which I'll get into, we're going to try to minimize the L infinity norm of this sum. And when we do that, we're able to relate this question of choosing a permutation of examples that minimize this running sum to a classic combinatorial optimization problem called the herding problem. So the herding problem is the following. So we're given a bunch of vectors, x1 through xn, all of which have bounded L2 norm. In fact, their L2 norm is bounded by 1, so they're all at most unit vectors. And their average is x bar. We want to find the permutation sigma of those vectors. So we want to reorder them in such a way that minimizes the worst case difference of a running sum of these vectors from a running sum of the average. So here we're maximizing over all m between 1 and n, and then this summation is basically a sum of the differences between the ith example that we chose in our permutation and the average. And there are many equivalent ways that you can present this problem. But the really cool and kind of surprising result is that it's actually possible to bound this as O tilde of 1. And one way to think about why this is kind of surprising is that if you have just a random permutation, if you just choose the order at random, it's pretty easy to see that this will be big O tilde of square root of n, right? Because if it's just a random ordering, then, well, if we think about the first half of the permutation, that's going to choose a random subset of the vectors. And it's pretty easy to see from like a variance argument that that's going to scale, or the variance of that is going to scale with the number of vectors that we sum, which is n over 2. And so the square root of the variance, which is going to determine this error, will scale as square root of n. And so the fact that we can do this with only log terms is pretty surprising and a really nice result. And so what we were looking into is how we can take this insight from the herding problem and use it to produce a faster rate for stochastic gradient descent. And one other thing to note is that the analysis for random reshuffling essentially goes through a bound of this type, and it gets that factor of big O of square root of n that I just talked about, which is what we would expect for random reshuffling to get over here. And that square root of n just ends up bubbling through the whole proof and appearing in the final rate. So there's some hope that if we got rid of that factor of square root of n, we would also make the factor of n in the final rate disappear. So we wanted to look at whether we can do this. And okay, in order to do this, we had to do a bit of a theory dive into how the herding problem works. So here's the idea. So we want to do this, and given some vectors, we want to find the permutation sigma that bounds the herding or the running sum by some quantity h of n and d. And this problem is related to another problem in combinatorial optimization called the vector balancing problem, which is very similar, except instead of finding a sequence of, or instead of finding a permutation of the examples that minimize this running sum, instead we take the examples in the same order that they're presented to us, but we're allowed to give them signs. So we're allowed to either add them or subtract them, or multiply them by +1 or -1 before adding them to the accumulator. And the vector balancing problem has a really nice, fast online solution that yields an L infinity norm of log of nd, which is pretty nice. And a sketch of the algorithm, which we can actually use to show that it's super fast, is that you start with an initially 0 accumulator S. At each step, when you're given a new vector xi, you basically choose the sign by first computing the inner product of xi, which is the next vector that you want to decide its sign for, and the current accumulator. And then you update S by either adding or subtracting xi from it, depending on the sign that you found. And I'm being purposefully vague about how the algorithm chooses this sign. It's actually not that complicated, but it involves a little bit of like scalar arithmetic and random selection. And for the purposes of what I'm trying to illustrate here, how it chooses the sign is not important. The only important thing is to note that the actual cost of doing this update is very low. The only thing that's costly here is computing this inner product between the accumulator and the new vector xt that we're getting, which can be done in time proportional to the dimension. So what's really nice, a really nice result from previous work, is that you can actually do herding. You can solve the herding problem with the vector balancing algorithm. And so this is actually a simplified version of the algorithm that we presented in our NeurIPS paper last year. So this is something that we've further improved it, leveraging some nice insights from the paper kernel thinning by Duvety and Mackey. And here's that way that you do it. So imagine that you have an even number of vectors, all of which have norm less than or equal to 1. We construct the sequence of differences of pairs of consecutive examples. So yi is equal to x of 2i minus x of 2i minus 1. We run a vector balancing algorithm as a subroutine on y, producing our signs epsilon1, epsilon2 through epsilon n. Then for I goes from 1 to n, we're going to set zi to be equal to x sub 2i, and z to the 2n plus 1 minus I to be equal to x sub 2i minus 1 if epsilon I is equal to 1, and vice versa otherwise. Essentially what we're doing is we associate each consecutive pair of examples with their difference. We find a sign for that difference, and then depending on the value of that sign, we keep one of the elements of the pair at the beginning of the permutation and put the other element of the pair at the end of the permutation. So, for every pair that's in our current order, one of them is going to stay in the first half of the new order permuted sequence Z, and the other is going to go to the second half. And what we can observe here is that when we look at the value of the ith element of the new permutation, what that's going to be equal to is it's going to be equal to 1/2 times the sum of the elements in the corresponding pair of the previous permutation x plus the sign that we got times the difference. And the easiest way to see this is to note that x1 plus x2 minus the quantity x1 minus x2 is just equal to x2 times 2, and vice versa. And so because of this, it's actually pretty easy to show that the sum of the first m elements in Zi minus their average is going to be equal to 1/2 times the sum of the first 2 elements in Xi plus the sum of the first m elements in Yi. And again, here, just to be explicit, Zi is going to be a new permutation of the same vectors. Xi is the original permutation of those vectors, and Yi is a sequence of differences. And because we inherit our bound from this vector balancing algorithm, we can replace this second term with whatever bound we got from the vector balancing algorithm. And now what this has given us is this nice recurrence relation. This says that if we run this whole process once, all this bulleted list, this whole process, then what I get at the end of the day is a new permutation of these examples Z, which has bound in terms of the L infinity norm less than or equal to 1/2 times essentially the same bound for the previous permutation plus this additional error that you get from the vector balancing algorithm. And then it's pretty easy to see that if you run this many times, we can get H that is arbitrarily close to the vector balancing bound. So this whole process shows that the herding bound that you can get is the same as the vector balancing bound. And this is a really nice theoretical result that solved a long-standing question in combinatorial optimization. So, okay, but then why should we care? How can we use this to improve our SGD? Well, the idea is that we can use this whole gradient balancing approach to get a better order by maintaining a permutation and iteratively improving it. So here's the idea. Here's the algorithm. We call it GRAB, gradient balancing. We start with just some arbitrary permutation of the data. Usually this is just the permutation, like a random permutation. Now, when we get 2 new example gradients, so gradients for 2 examples that are consecutive to each other in the current permutation, we pass their difference to an online vector balancing algorithm that we're running in parallel with the optimization loop. And then if the sign is +1, we append that example to the beginning of the next epoch's order and prepend the first example to the end of the next epoch's order, and otherwise we do the reverse. And so what we're doing here is we're constructing the permutation to use for the next epoch as we're running the current epoch. And the nice thing about this is that it has very low overhead. So it has a memory overhead proportional to D, the problem size, the dimension, because it all we need to do to store new things is to store the accumulator used by the online vector balancing algorithm, and that just takes time proportional to the dimension. And similarly, it takes only compute overhead proportional to ND per epoch, because, well, all we're doing is we're doing this work that's proportional to the dimension once per example. And that's pretty cheap compared with the cost of computing gradients for the whole epoch. And the nice thing about this is that we're able to get some cool convergence rate bounds. So if we bound the gradient error, so we suppose that every example gradient is within a error-bound sigma of the full batch gradient. And we assume that we have this sort of special cross norm L smoothness, which is that the difference between two gradient values in the L2 norm is less than some constant L sub 2 comma infinity of the difference between their weights in the L infinity norm. This, it turns out, holds for a lot of problems where the examples are sparse or where the gradients are low rank under standard conditions, but even in the worst cases, only loose by some factor that depends on the problem size. Then, after nk total iterations, or where n is the size of the problem, and n is the number of examples, and k is the number of epochs, gradient balancing gets a bound on the average gradient magnitude squared proportional to L to the 2/3, sigma to the 2/3, t to the minus 2/3. And if we ignore problem parameters like L and sigma, and we just look at the dependence on t and n, we see that here we get big O tilde of t to the minus 2/3, and this is an improvement over big O tilde of n to the 1/3 t to the minus 2/3 that you would get from random reshuffling. And so gradient balancing will generally tend to be better in cases where, at least in theory, in cases where this cross norm L smoothness constant is small relative to the L2 smoothness constant times the square root of n, which generally happens when the dimension is small relative to n or when the gradients are sparse. But in practice, it turns out that even in cases where we don't have like either of those properties, gradient balancing still works really well. So here's a really dumb example for logistic regression on MNIST. And we can see that if we compare, shuffle once, random reshuffling, this other example order method called flip-flop, and gradient balancing does substantially better, both in terms of training loss and eventual validation accuracy on even this relatively simple problem. And just to explain, greedy is like a simple algorithm based on just solving the herding problem independently at each step using at each epoch using a cached save of all the gradients that happened in the last epoch. So it's you can think of it as a more naive and much more costly from a system side version of the algorithm that I just described, which we're including as an ablation. But isn't really relevant to what I'm saying in this talk because I haven't talked about that ablation. More important is how this works for deep learning, because that's really what we care about for large-scale optimization. And here we can kind of see that for this LSTM on Wikitext 2 and this BERT model, we do get significant improvements over random reshuffling and shuffle once and other baselines just from running this example order refinement method. So one final thing that's kind of ongoing work that is in submission is how to potentially make grab more well distributed. So remember at the start of the talk, I talked about how one motivation for this line of work was being able to choose example orders that are, or analyze example orders that are maybe more amenable to computation on workers, depending on where the examples happen to be physically located. And this is a problem for grab because when we run gradient balancing, it can choose an example order that's arbitrary. It can be any order. It doesn't necessarily conform to any particular location or partition of the data set. And in distributed learning with decentralized data, we would like every mini batch to include one example, or at least the same number of examples stored on every worker. And that's not going to be guaranteed to be the case for an example order produced by gradient balancing. So we figured out a kind of new way of doing this. And since I think I'm running out of time, I won't go too deeply into how this works. It uses the same idea of balancing pairs, but instead of balancing pairs that are consecutive to each other in some global example ordering. Instead, we're balancing pairs that are consecutive to each other in the order that is presented on a single parallel worker. And this lets us get a nice, almost linear speed up. So the rate that we get is, again, bounding the same square of the gradient of the loss. The dominant term is 1 over nk to the 2/3, where k is the number of epochs, n is the number of machines, and m is the number of examples per machine. And this yields real linear speed up in the dominant term, which is really nice. We're not giving up anything in order to get that parallel speed. And here's some nice results. So distributed gradient balancing for this LSTM task outperforms random reshuffling and other incremental approaches on both training loss and perplexity. Okay, so the takeaway, and this is all still ongoing work, so we're going to be realizing more and more of this improvement, but kind of the takeaway is that there's lots of potential improvement that we can make from using better example orders than what we get from just selecting it at random. And we can actually get improvements in the rates that we get, not only in theory, but also in practice, by trying to understand these problems theoretically. And so there are a bunch of next steps that we're working on. So we're trying to use this stuff for quantization. We're trying to use it for fine-tuning large foundation models, where we might want to run a small number of epochs, so potentially only one epoch. And we're in the process of releasing efficient implementations of all this stuff. And our implementation of Grab is already on GitHub, so you can download it and use it and accelerate your own large-scale optimization. So thank you. I'll stop here and hopefully have at least 10 minutes for answering questions left in the slot. But just to recap, or maybe zoom out a bit, there's a bunch of other stuff that we do in my lab. So I also work on decentralized learning, manifold learning, accountable machine learning, quantization and compression, and on statistical inference using Markov chain Monte Carlo. So I'll stop there, and hopefully this will be enough time for questions.